into applications of derivatives. We've seen how to take derivatives. We've done implicit differentiation, logarithmic differentiation. We've learned a ton of derivative rules. We've seen how to take higher order derivatives. And today we are going to be moving into seeing how derivatives affect a graph. So or rather what derivatives tell us about a graph. So we're going to be looking at increasing, decreasing, maxima, and minima. So our goal for the next few classes is to understand how derivatives and second derivatives affect the shape of a graph so that we can eventually build up to using information that we get from the derivatives to graph functions that are actually quite challenging to graph, that we wouldn't be able to graph based on what we already have. Okay, so that said, we're going to start off with like a little theorem, or rather a definition here. And we're going to do that by looking at a graph. So let's say that this is a graph of a function. This part right here, where as my x values get bigger, y gets smaller. We say that f of x is decreasing. And so it kind of makes sense. It's going from like left to right down. We say that the function is decreasing there. So as x gets bigger, y gets smaller, we say f of x is decreasing. Over here, as my x value gets bigger, my y value also gets bigger. And in this case, we say that f of x is increasing. I'm having some writing trouble today. So here, we call this increasing. And then on this line right here, what happens to my y value as x gets bigger? If I look at like what I've just kind of gone over in red there, as my x value gets bigger, it doesn't change. You got it, Mikhail. It doesn't change. So as x gets bigger, y doesn't change. We say that f of x is constant. So f of x is constant. And if I go over here and I look at where it's increasing and I draw a tangent line at a place where it's increasing, is the slope of that tangent line I drew positive or negative? It's positive. That has a positive slope. And what's another word for the slope of the tangent line? Derivative. You got it. So here my slope is positive, which means that my derivative is positive. What about where it's decreasing? If I were to draw a tangent line here, is the slope of that tangent line positive or negative? So here the slope is positive, negative. The slope is negative, which means that the derivative is negative. And what about here where it's constant? If I draw my tangent line there, what's the slope of that tangent line? That tangent line is horizontal. What's the slope of a horizontal line? You got it, Marino. 0. So here, the slope is 0, so the derivative is 0. So in other words, there's this relationship between the sign of the derivative, is it positive or is it negative, and whether or not the original function is increasing or decreasing. And this is actually a specific test that's called the test for increasing and decreasing. And so what this test tells me is 3 different things. The first is that if the derivative, so if f prime of x is positive, so greater than 0 on some interval, so for all x on some interval, then the function is increasing on that interval. Then it tells me that if the derivative is negative on an interval, as we can see up there, a negative derivative happened when it was decreasing. So if it's negative for all x on some interval, then f of x is decreasing on that interval. And then the last thing is that if it equals to 0 on an interval, then f of x is constant. And this is my test for increasing and decreasing. And this is really nothing that we haven't understood just from like looking at that graph and understanding what the derivatives look like. So what we just stated really what we already know as kind of like a rule. So that said, the question then becomes, how can I apply this rule to figure out all of the places where f is increasing and decreasing? So I'm going to go up here and we're going to start kind of thinking of increasing with an arrow like that and decreasing with an arrow like that. So that way when I'm talking about increasing and decreasing, we can kind of just use these little arrows. So increasing, decreasing. Okay. So let's go back and look at the graph that we have. Our goal to answer this question, how can I apply this rule to find all the places where f of x is increasing and decreasing? Our goal is going to be to try to find all possible places where it might change from one to the other. Okay, so let's take a look at these two graphs and try to figure out what's happening at the places where it changes. So in this first graph, I just redrew the graph that we did the first time around. The places where it's changing are these things that I've circled here. What is the derivative equal to at those two places? Or rather, what do we have at those two places? What is this? What is that? You got it. It's a cusp or a corner. And does the derivative exist at those places? No. So here it changes at a cusp or a corner where the derivative does not exist. So let's look at this second graph. The first place I change from increasing to decreasing is right there. What's going on right there? What does my derivative equal right there? You got it, 0. Hang on 2 seconds. So exactly, so there the derivative is 0. What about here and here? What's going on at those other two places where it changes? What's the derivative there? Ah, oops. So right here and right here. So Dina, you may be talking about right here, but at each of these places, my derivative, I have a horizontal tangent line and the derivative is 0. So at those places, the derivative is equal to 0. And what about at this place right here? What's happening? At the place that I've circled there. A discontinuity, I have a jump discontinuity. And does the derivative exist at a jump discontinuity? You got it. So jump discontinuity. And here the derivative does not exist. So what we are seeing is that there are two different types of places where the derivative where the function can change from increasing to decreasing. And those two different types of places are when the derivative equals to 0 and when the derivative does not exist. And these specific x values where this happen are called critical points or critical numbers. So definition. A critical number And you will sometimes see critical numbers called critical points or critical values. A critical number is a value C where f prime of C is equal to 0 or f prime of C does not exist. So in other words, critical numbers are values where there are horizontal tangent lines or cusps, corners, discontinuities, vertical tangent lines. Now we're going to do a little like caveat here that we're not going to think about much, but it's still important to write this. A value is only considered to be a critical number if the function is defined there. We're going to write that down so we have it, but largely we're going to ignore it. So also, something that we're not going to ignore, but that we're going to use all the time is that we just saw that these values are important. They're called critical because they're where things happen. So it turns out that a function can only change from increasing to decreasing at these critical values or at these values where the derivative does not exist or equals to 0. Okay, so these critical values and the fact that they are the places where we change from increasing to decreasing allows me to come up with some guidelines for how I can apply that test and answer the question we started with, which was, how do I find the places where it's increasing and decreasing? So the first thing that we want to do is, if I know that it can only change at critical values, then I need my derivative. So this tells me that the first thing that I want to do is find the derivative of f. And the second thing that I'm going to want to do is find the critical values. So find the values where f prime of x equals 0 or f prime of x does not exist. This f prime of x equals 0, this is like the thing that we've been doing all semester, finding our horizontal tangent lines. And this is like setting the denominator equal to 0. Then our third step, we're going to set up something called a variation table, or rather a table of values. We're going to create intervals using the values from step 2. Oops, we're doing using to find. At one point, so we're going to create intervals using the values from step 2, and then we're going to use a table of values, which you'll often see called a variation table, to find the sign of the derivative at one point on each interval. Then we're going to use our test to make a conclusion. Okay, so these are our guidelines. We're gonna now do a problem. Let me know in the chat when you've got the guidelines down and you're ready to start a problem. A lot of you guys ready. So we're going to find, actually we'll do this in black. Find the intervals where f of x is equal to x to the 4th plus 1 over x squared is increasing and decreasing. Okay, so our first step tells us that we want to find the derivative. Now, question, if we're asked to find the x values of horizontal tangent lines, do we need to simplify? If I were to like I'd tell you find the horizontal tangent lines, would simplification be part of that problem? Think about what you guys did on your midterm. The horizontal tangent line question, did you need to simplify? Yes. Yes. So here, I'm going to put in parentheses because sometimes it's not going to be that important, but for the most part, we're treating this as a horizontal tangent line question. And in horizontal tangent line questions, we need to simplify. So we're going to put simplify in parentheses up here. So my step one is to find the derivative. What rule do I need to find the derivative? The quotient rule, you got it. So f prime of x is equal to the derivative of the top, 4x cubed, times the bottom, minus the top, times the derivative of the bottom. All divided by the bottom squared. So that's x to the fourth there. Now this is definitely not simplified as it is. So what's our greatest common factor of the numerator? What's the greatest common factor of the numerator here? Is it just x? Is there also a constant I could bring out? You got it, there's a 2. So in that 4, I can think of 4 as being 2 times 2. So the greatest common factor of the numerator would be 2x. So I'm gonna factor that out, and that's gonna give me 2x times 2x to the fourth minus x to the fourth minus 1, all over x to the fourth. And so be careful about this minus sign. It kind of got distributed inside of that x to the fourth plus 1 there. So then this is 2x times x to the fourth minus 1 over x to the fourth. What can I do here? Can I cancel out one of those x's? Yes. So I'll have 2 times x to the fourth minus 1 over x cubed. Okay, so now in my second step, we want to find the values where f of prime of x equals 0 or f prime of x does not exist. And up here, I'm going to put in parentheses that what we're doing is finding critical values. And it's going to be important. You're going to see the word critical value used over and over again. So here, in other words, we're finding critical values. I wrote a 1 in there, that should be a 2. And so to find these critical values, we know that they occur in 2 different places. The first is when f prime is equal to 0, and the second is when f prime does not exist. So I need to find where both of these things are happening. To find where it equals to 0, like with horizontal tangent lines, that's what we're doing here. Remember, that's like setting the numerator equal to 0. Because the denominator isn't going to give me information about when this thing equals 0. So if I'm like x squared over 2 plus x equals 0, that 2 plus x doesn't matter. I'm only looking at where the numerator equals to 0. So in the same vein, f prime does not exist. I only care about division by 0 here. So this is going to be like letting the denominator equal to 0. So over here, I'll say 2 times x to the fourth minus 1 is equal to 0. Which gives me x to the fourth is equal to 1. What values is that going to give? When does x to the fourth equal 1? Definitely a positive 1. What's negative 1 to the power of 4? You got it, Gwen. So this is going to give me x is equal to plus or minus 1. So anytime the power is even, we must do plus minus. Good. So then f prime does not exist. That's like setting x cubed equal to 0. What value do I get there? When does x cubed equal to 0? What number am I going to get? Got it. So this will give me x is equal to 0. So here I got 3 critical values. They are x is equal to -1, 0, and 1. So that brings us to our step 3. I didn't do x to the 4th equals 0 because when we look at my final derivative here, this was my derivative. I don't have an x to the 4th in the denominator. I don't have a factor of x to the 4th anywhere. I have a factor of x to the 4th minus 1. So here, it's like I set the numerator equal to 0, so that was 2 times x to the 4th minus 1, which gave me x to the 4th minus 1 is equal to 0, but then I didn't have an x to the 4th. So I'm really only looking at the derivative. Does that make sense? Does that make sense, Gwen? So really, we're only just looking at the final version of the derivative. Good. Now, step 3 says, step 3 is going to be a little bit confusing the first time we see it. I'm creating intervals using these values, and I'm going to create a table of values. So in my step 3, my table of values is going to look like, I'm going to write I here for interval, and in the future, I'm just going to write I. And I'm going to create intervals using that table of values. So I'm going to start at -infinity, and I'm going to get up to the first value that I have. So the first value I have is -1. And then my next interval, I'm going to start where I stopped and go up to my next critical value. And then I'm going to go from my next critical value to my next one. And then I'm going to go up until infinity. So notice that I'm separating the intervals. I'm just separating off using the critical values. And I always start where I stopped. So in the future, in our table of values, we're just going to use the letter I. Now my next row in my table of values, I'm going to call test value. And in my test value row, I'm going to pick a value on each interval. So what is a good value between -infinity and -1? -2. So that's what's going to go in my table of values. Between -1 and 0, -3 also works, Dean. It's a good value between -1 and 0. You got it, Dean. -1/2 would be a good value. -1/2, 1/2. And you guys know I hate decimals, but this is one time where decimals would be okay because they're not part of our final answer. They're just to get a feeling for, well, to get a feeling for the sign. So then here I'm going to pick 2. And then my third row will be sine of f prime of x. And what we're doing here is we're looking for how to apply the test for increasing, decreasing. I'm just going to go up for just a second. Remember, the test for increasing, decreasing gives me information about f based on the sign of f prime. So I need to know, is f prime positive or negative on these intervals? So then here, what I'm doing for the sign of f prime is I'm plugging the test values in to f prime to get a sign. So my f prime was 2 times x to the 4th minus 1 of x cubed. So I'm just going to rewrite that. F prime of x is equal to 2 times x to the 4th minus 1 of x cubed. So then I'm looking at f prime of negative 2. And this is going to be similar to the thing we did before when we were doing limits that gave us a constant over 0. I only care about the sign. So you can plug this into your calculators, but a good way to deal with this would also be to look at the sign of each factor. You got it, Dean. This one's going to be a negative because I'll have a positive over a negative. So then up here, I'm just going to put a negative in my table. And then I'm going to look at f prime of negative a half. And I'm going to get 2 times negative a half to the 4th minus 1 over negative a half cubed. And that's going to give me positive negative over negative, which is giving me a positive sign. And then we're going to do the same thing with 1/2. F prime of 1/2 is 2 times 1/2 to the 4th minus 1 over 1/2 cubed, which gives me positive negative over positive. So here I'm back to having a negative sign. And then f prime of 2 is 2 to the 4th minus 1 over 2 cubed, which gives me positive, 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 and I'm back to having a positive sign. And then our last row will be, actually, we're just going to write f of x, and we're going to make our conclusion. So in our last row here, this is actually our step 4, where we apply the test for increasing and decreasing. Is it increasing? Is it decreasing? Okay, so when the derivative is negative, did we say that the thing is increasing or decreasing? What did our original test for increasing, decreasing tell us when the derivative was negative? You got it, decreasing. So here I'm going to write decreasing. And when the derivative is positive? Increasing, you got it. And so suddenly I have my intervals of increase and decrease. So here, our final answer is that it is increasing on -1, 0, and then we put union 1, infinity, and it is decreasing on -infinity, -1, union 0, 1. And this is my final answer. Okay. Are there any questions about what we did to make this conclusion, how we applied the test and followed those guidelines? The rounded ones mean not including. So square brackets would mean including. So like you guys might have seen this before as backwards brackets like that. If I'm not mistaken, that's how they do it at French school. Oh, there, now they showed up. Okay, any questions about this? Okay, so it turns out this increasing and decreasing is actually not the only conclusion I can make from this table of values that I have. So we're going to learn something else and then go back to this table of values and make some other conclusions based just on the information that we have right here. So we're going into a section now that's called extrema. Uh-oh. I don't know what just happened. Give me a second. My iPad just started updating itself like right now. Lovely. Give me a second. This is perfect. Okay, we're gonna quit that. It's not connecting. We're gonna do this. Okay. Okay, that worked. Now, lovely. All right, do you guys see the screen again? Okay, good, awesome. So extrema. So what extrema is maximum and minimum of functions. So we have two different types of extrema. We have something called absolute extrema, which is also sometimes known as global extrema. So this would be absolute maximum and absolute minimum. So a function, f of x, has what's called an absolute or a global maximum at x equals c if